You'll notice I'm not wearing my coat today. It's hot and humid, way too hot and humid for a sports coat. So I am just in a t-shirt. I spoke with Neal this morning. He said to say hi and did send his regards. And so in his place, I will not be giving his talk, but rather another talk. Interestingly enough, this does relate to software architecture metrics, and you'll see why about halfway through. So I tried to find something that still worked on the theme. And this is about modularity versus granularity. Now we're going to be, this here, there we go. I'm going to be referencing a lot of this material actually comes from the book that Neal and I just wrote last year, the architecture, the hard parts. And so I'm going to draw some material off of this. When we talk about modularity, as Ekaterina said, modularity is about the breaking up of our systems into multiple parts. But granularity is about what size those parts should be. And these are two very different things. Those of you who do follow me on Twitter will notice one of my quotes, embrace modularity, but beware of granularity. Because it's with granularity that we usually run into trouble. So I want to talk about both of these, and as a matter of fact, let's start by talking about architectural modularity, that breaking apart of systems into multiple parts. I want to talk about two parts. Why should we break apart our systems? And how should we go about doing it? So let's talk about modularity first, and then we'll talk about service granularity after this. Certainly, all of you will probably agree that it is definitely a trend, because most companies are involved with taking our large monolithic systems and breaking those apart into smaller deployment units, microservices, for example. Why are we doing this? It's so much pain, it's so much cost, it's so much effort, it's so much attrition. Well, let's find out why. So what does this knife do? And that's a very easy question. It cuts things. That's what it does. And we release this knife into production. Okay, but guess what happens? Like our systems, customers want more. New features so that the knife becomes more usable, like our systems. And what happens? The knife starts to grow to add additional features. Now that I have scissors and a file, instead of that single blade, I'm not lopping off the ends of my fingers and toes when I'm trying to trim my toenails or fingernails. But what happens? Customers want more. And like our systems, this knife starts to grow into something a little more usable now, something that I have a few more tools that I can use. However, you guessed it, well, this is useful, and now I can actually open up a bottle of wine or a beer and stuff like this. This is kind of just an all-purpose knife. But my favorite activity is hiking. And while this knife is good, it doesn't contain all the features I need while I'm doing backcountry hiking or camping. So guess what? Like our systems, customers want more. And the knife starts to grow into something like this. Now, this is the pocket knife that I have. However, I no longer put it in my pocket because it weighs too much. It goes in my backpack. But now I've got all sorts of really useful tools on here. Until guess what happens? Like our systems, over years, customers still want more. And over time, that knife grows into something like this. Now, believe it or not, this is an actual knife you can buy. But it's no longer going in my backpack because it weighs too much. As a matter of fact, you know what is absolutely amazing about this knife? It's still a knife, but you can barely notice it. This is one of the reasons for architectural modularity, because our systems do grow with additional features, additional lines of business, acquisitions, that happen to do additional functionality. And we continue to bolt it on to our monolithic applications until it looks like this, something completely unusable. Okay, but let's go back to technology, because the other why question are all of these architectural characteristics that are not supported in our monoliths, but they are supported when we break up into architectural modularity. Maintainability, the ability to change code quickly, find out where the code needs to be changed, and change it effectively. Testability, the ease of and completeness of testing. Much better to get completeness and ease of testing with a small, single-purpose service than a large monolithic application. Deployability, which is about three things. It's about the ceremony of deployment. It's about the ease or ceremony. It's about the frequency of deployment. And also about the risk of deployment. How often do you deploy your large monolithic single deployment applications? Every week, 2 weeks, once a month? Do you realize with that little frequency, we don't get, as developers, a lot of practice deploying software. But move to this level of modularity, and we do. We can deploy on a daily basis. That's practice, everyone. And also a lot less risk. And finally, of course, scalability and fault tolerance. Okay, but what about the how? So those are the drivers for the why. But let me show you a flow chart that Neal and I put together to really kind of guide us about, I got it. Yeah, we need to break apart our systems. But how do I go about doing it? Well, the first thing we ask is modularity even justified? I just showed you 5 main drivers to move to architectural modularity, microservices. Do you need any of those? If not, then keep it a monolith. Back-end settlement systems, back-end reconciliation systems do not need to be microservices, generally speaking. The other thing we ask, is it even feasible to decompose our systems? Maybe it's not. And in which case, if it's not even feasible because we don't have the source code anymore, or it's a big ball of distributed mud that we don't understand, then keep it a monolith. But if it is, then we have a choice. Do we have definable architectural components inside our application? If we do, then we can use something called component-based decomposition. Otherwise, we go to tactical forking. And this leads us towards a distributed architecture. Well, let's take a look at each of those approaches very briefly here. So component-based decomposition. Now this, by the way, does happen to be the largest chapter in our book. When I wrote that chapter, it started out at about 90 pages. And of course, I had to whittle it down from there. But that's how much detail is involved with these patterns of decomposition. But I want to show them to you very briefly to compare them against other approaches. So these architectural component-based decomposition patterns are a series of controlled, iterative steps of refactorings of your application to eventually get to a place where we can actually extract services. And through these series of steps, we take our system, our current application, which is a monolith, and we start using or applying some of these patterns to refine our architectural components as well as our domains to be able to then extract those domains into domain-based services. And from there, move to microservices. Okay. Let me show you a different approach. Let's move from component-based decomposition, slow, controlled refactorings that improve the quality of our monolithic system while we are decomposing it, allowing us to extract. Sounds fairly low risk. which it is. The trade-off, it takes a long time. Let me show you a different approach. It's called tactical forking. Now, what I just showed you in these component-based decomposition patterns, which would be a great workshop next year. That would be fun. Maybe we'll do that next year. But I just showed you extraction, where we do refactorings to get what I at least consider a clean architecture, to where I can just extract fairly simple, a lot of right-click refactor moves. However, tactical forking is actually not about extraction, but rather replication and deletion of the things you don't need. When we apply tactical forking, essentially all of us become sculptors. We're given a block of marble or granite or ice like this, and we chip away at the stuff we don't want, arriving at the beautiful sculpture, which ends up being our service. Let me show you this approach. So when I say forking the application, I really do mean replicating it. We have multiple teams working on the same monolithic system. We replicate that repo, copy it over to here. And now we have one team working on this repo, another one working over here. And then each team works as a sculptor, saying, well, that's not part of my functionality. No, that's not what I need. And they continue to sculpt until they arrive at the service they want. Let me show you and animate this process of tactical forking. So we start with our monolithic system, and we literally replicate it to other repos. Copy of that system. So now, if we're going to personify this in the room, we would have 1, 2, 3, 4, 5, 6 different copies of it. Now, are you ready? Each team, get your chisel, because we're going to start chipping away. And notice, oh, but stop. Did you notice what just happened here? We have to know what we're sculpting. This is one of the first biggest differences between tactical forking and component-based decomposition. You see, with component-based decomposition, it evolves. I don't know how many services we're going to have. I don't know what they're going to look like. We're going to continue to do refactorings using these patterns to group-like functionality, analyze dependencies, analyze cohesion, and arrive at the services. Here, if we're going to sculpt something, that would be like me giving you a block of granite and saying, go ahead, Mark, what would you like me to create? I don't know, figure out something. Yeah, that's not going to work. Because halfway through that sculpture, you're going to say, I don't like this. Well, it's now too late, because you've already carved off the pieces that you now need for the other idea you had in that marble or granite. But that's the first thing. We need to know what services we're carving. For example, we're taking our monolithic application and we're dividing it here into reporting, ticketing, and customer service. Now we can sculpt. Ready, set, go. And each team just starts chipping away at the stuff they don't need. This is a really effective technique. If we don't have well-defined components, if we're ending up with a big ball of distributed mud that we have to somehow just figure out what to do, or we don't have a lot of time. Because this approach, folks, is fast. However, there's another negative here. And that is, because we're replicating, we have to deal with all the common and shared code. A lot of trade-offs between these approaches. Welcome to architectural modularity. Either we take a slow, controlled approach and it takes a long time to refactor and arrive at microservices, or we do it really fast, but we end up with a mess of duplicated code everywhere. All right, let's actually now take a look at granularity. So that little journey we just did was all about architectural modularity, the breaking apart of our systems. and we have. But how large should those pieces be? How small should they be? When we do microservices, all of us in this room know that the word micro means small. But how small is small? How big is small? This becomes quite a challenge when we try to figure out how big our services should be. So, now I get to talk about software architecture metrics. This is cool. It turns out that there are two forces at play when arriving at the right size or the appropriate size of a service. The first are a set of drivers called granularity disintegrators. These are drivers I'm going to show you that basically tell you, yes, you should break apart your service into smaller pieces. However, we have to balance those with corresponding trade-offs of granularity integrators. Those drivers that say, not so fast. I think we should keep that service together or even maybe combine multiple ones. Arriving at the right level of granularity is about achieving a balance between these drivers. So let's take a look at them. I'm going to show you 5 disintegration drivers. The first one is the usual and typical go-to when we start addressing service granularity, and that is service functionality. In other words, single responsibility principle. A microservice is defined as a single-purpose function, separately deployed, that does one thing really, really well. Great definition. Or is it? Most business applications have a notification service, a means by which we can notify our customer through texting, email, even postal letters that we still get in the mail. Let me ask all of you a question. Should this be a single-purpose service based on notifying a customer? Or should we break it up into 3 based on the service functionality? In other words, let me ask you the question a different way. Which in your mind is single-purpose? Notifying a customer or notifying a customer via SMS texting? So, gut feeling based on single responsibility principle, SRP, the S part of solid. Show of hands, just gut feeling. How many of you would keep it a single service, notification? That's single purpose. Brilliant. How many would break it apart into the 3? Okay, fantastic. So this was a little more interesting. I do this poll all of the time, and it usually ends up 50-50. And we had about 1/3, 2/3. What are you going to do then? Because half of your team feels that it should be one service, but the other half of your development team thinks you should break it up. How are you going to resolve this conflict? This, folks, is exactly the problem with service granularity. I did tell you that this talk would align with kind of the theme of GSAS, which was software architecture metrics. And here's where it comes in. Let me show you 4 other drivers we can use that we can objectively do measurements to determine whether we should break apart a service. You see, single responsibility principle, service functionality, cohesion, these are all the same thing, is too subjective. My opinion is that we keep it one service. Your opinion is that that's too coarse-grained. It's not single-purpose enough. Do you notice the word I used? Opinion. Let me show you 4 other ways what we can measure. And the first of those is code volatility. This is very similar to volatility-based decomposition. So let's go back to our notification service. One of the things I can actually measure fairly quickly is this. Are there areas of the code in this single service that change more rapidly than others? And in fact, I do a simple git command, retrieve history from the last 2 years, format it really nicely, and here's what I find out. The code in text and email, folks, rarely changes. As a matter of fact, according to this report, which I can show you, this is not just opinion, it's been 9 months since that code changed. However, the code in letter, not surprisingly because we all kind of knew it, but at least I can demonstrate it through a report from a query, that changes 1 to 2 times a week on average. Because you see, all of our letters are manifested through class files. And the legal team is continually changing the grammar of our letters. Now, anybody think data-driven might be a better approach for this? Yes, but it's not right now. So, what happens in this single service? First of all, 1 to 2 times a week, I've got a larger testing scope. I have a responsibility for testing, texting, and email because I might break them. My deployment scope is also a lot broader. I've got more deployment risk, and watch this, if I can't do a hot deploy, that means 1 to 2 times a week while I'm deploying letter, SMS texting, and email are not available. But if I break these up into 2 services, I've isolated the code change because the code rarely changes in notification, electronic notification, but it changes all the time in letter. Smaller testing scope, less deployment risk, and when I deploy, I'm not impacting text and email anymore. That's really hard to argue against, isn't it? That's what I mean about objective metrics that now justify no discussion. It's like, yeah, okay, let's do it. Next. That conversation, which took a week on the prior driver, now takes about 5 minutes. Okay. Let me show you another disintegration driver that we can also measure, and that's scalability and throughput. Do all the pieces of this single service scale the same? As a matter of fact, let's go back to notification. I love picking on this service. This is something I can measure. What's the throughput requests based on different functionality? And I do. And as a matter of fact, here are the results, folks. We send on average 220,000 texts per minute, 500 emails per minute, and on average, 1 letter a minute. What does this single service have to scale to? All that functionality has to scale to 220,000 requests a minute. But it gets more interesting than that, because yesterday I talked about a metric called mean time to start when we were looking at that test taker. And this impacts elasticity or responsiveness. Because look at how many texts I send, and this is due to mostly multi-factor authentication. Well, if I get a burst of users trying to sign in, how fast can I respond to that? Unfortunately, this service right here takes 3,400 milliseconds to start. Now, SMS texting starts immediately, 200 milliseconds. Email has to set up all these SMTP connection pools, all these instantiations. Letter actually goes out and starts looking for broadcasts from printers and checks the health to make sure they're active, because that's what that functionality does. It prints letters. So, mean time to start, as well as additional cost of scalability, are good drivers to break this service apart into 3 different services. Now I can have 10 instances of notification, 2 instances of email, and I only need 1 instance of letter out there. A lot more cost effective, but better. Now, if I need additional instances for texting, which is where my throughput is, 200 milliseconds mean time to start. That's responsiveness. That's elasticity. Well, let's look at another driver that we can actually measure through metrics, and that happens to be fault tolerance. So let's go back to our notification service again. I like that consistency with that, because maybe we don't have any of those other drivers, and I'm still confused, Mark. I just don't know if we should split it up or not. Oh, well, one of the other things we can look for are error rates. Are certain areas of my service more error prone than others? And it turns out I can measure this through observability, and guess what I find? Not surprisingly, we already knew this, that email continually fails because of some memory leaks within the SMTP connection pool. We still can't find them. We're still looking. But guess what? The entire service goes down. We no longer have SMS texting. We no longer have email. Now I have to take 3,400 milliseconds to start up a new service. However, if I broke this apart to 3 services, now when email fails, it's not impacting any of the other functionality. A really good illustration and definition of fault tolerance. When faults occur, A, how fast can we respond to them? And B, what else is impacted when that fault occurs? This is great levels of fault tolerance. All right. Oh, hey, wait a minute. Did anybody notice something a little odd about this? I bet this slide generated a question, because I certainly have one. Mark, with the code volatility, you broke the service up into 2 parts. We extracted the volatile code into letter, but then we coupled the other 2 into electronic notification service. But here, you broke it up into 3. Yet here, SMS and letter, both are reliable services. So why did you break those apart? Why not do the same thing we did with volatility and just make those one service? Here's the answer. And the answer is in the form of a question to you. What would you call that combined service? Non-email service. Lovely. Yes. So self-describing. What does this do? That does email. What does this do? Non-email. All right. Now I got to go look at the code because I just don't know what kind of forms it does. Yeah. So non-email, that's a vote. Okay. Any other ideas? SMS letter service. No, it gets even better than that. For those of you in spring, you're like, yeah. SMS letter notification service. Wonderful. Great. Next week, we're going to start notifying through Facebook Notifier. And then through Slack the week after. Now what do we do? SMS letter, Slack, Facebook notification service. Yeah, we're back to non-email now. Do you see the problem? We are actually traveling back to the first driver. Cohesion. Service functionality. That has low cohesion. And here is the trick. So I kept it as 2. Here's the good test for you. If you have trouble naming a service, chances are it's low cohesion and should probably be multiple services. All right. Well, there is one more disintegration driver I want to show you, and that has to do with request access, security. Another good disintegration driver. We're going to do a different service this time, a customer profile. Now, this service handles all of my profile information, my demographics, my address, my avatar, billing address, so on and so forth, and all my credit card information. But we know the credit card information, we want to restrict access to that. So we have requests coming north-south, meaning from a user interface. and also requests coming what's called east-west, inter-service communication. What are the chances that a request meant for profile information can get into the credit card information functionality, and hence the credit card data? Oh, it's not possible. I've written code to prevent that. Folks, that bad request, that rogue request is already in that service. Good luck trying to protect that. However, breaking apart this service into a profile and a wallet service, now I have provided access control at the API level. You're not even getting close to that service functionality where my code attempted to prevent you from executing any of that. It's another good driver. So isn't that wonderful? Utilizing metrics, we can actually objectively determine whether we should break up a service or not. It's no longer an opinion or a guessing game or a coin flip, whatever techniques you use today to determine whether you should break apart a service. All right, let's drink shots. If I fall down, service stays one. If you fall down, we break it apart. Go! Oh, there'd be a lot of fun games we could probably do about that. Yeah, I'll make up some other kind of driver for that. But that's only half the story. You see, we've got good drivers to break apart a service, but we have to balance those with trade-offs from integration drivers. Those drivers that say, no, you should keep that service together. And there are 3 of them that I want to show you. First one has to do with transactions. So here's the example. Let's say that I've got a profile service and I've chosen to break up the profile and password information for access control and code volatility. And those are the 2 drivers. But what happens now when I go to register a new customer? Well, profile and security info, both encrypted, come into the profile service. That's where the API is pointing to the endpoint in the service. Profile service says, oh yeah, that profile information's mine. So it does the insert into its database. But this security info, not mine, so it sends it encrypted over to the password service. Now, the password service does what it needs to do for further encryption, tokenizing, and inserts it into its table. Yeah, that's how microservices works. We understood disintegration drivers for justifying that we should break this apart, but we no longer have a database or ACID transaction. We can no longer do commits and rollbacks. And if the business requirement is that this be in a single atomic transaction, a database transaction, where there can never be a case where we have an entry in profile that's not in password, and vice versa. That means I had some good drivers to break it apart, but now I need to put that service back together because transactions are more important than code volatility and scalability. So that's our first driver that we start to see. Let's take a look at the most common integration driver that exists. That's data. Isn't it interesting? I spent the whole time talking about functionality. And we always seem to forget there's this thing called data out there. Well, let's see how data relationships can impact our service granularity. So let's say I have a single service. It does functions A, B, and C. And it has a nice, well-formed, bounded context with this schema of these 6 tables. I go through all the various disintegration drivers, and I say, oh, yeah, this service should absolutely be broken apart into 3 parts. But the problem is now, all those parts are sharing all those tables, and we no longer have a bounded context. So let's build it. Okay, when you build bounded context, which means the service owns its data and owns its data structures, in order to control change in a highly distributed architecture. That's what the bounded context is all about in microservices. So let's do that. Now, generally, when we assign ownership to services, the owner of a table is the one who writes to it. Michael may depend on all of my data for his processing. It's like, Mark, you don't understand. No, I have to have your data. I mean, it is core to all of my algorithms and processing. He's like, well, that's fine, Michael, but I own it because I'm the one who writes to it. You're only reading it. So let's assign ownership. Function A writes to tables 1, 2, 4, and 6. Means it owns those tables, but also it reads from table 5. Okay, whatever. Function B writes to table 3, but needs to do reads from 2 and 5. Finally, function C writes to table 5, but needs to do reads from tables 1, 2, and 3. Okay. So we got all that down. Let's form our bounded contexts. The owner is the one who writes, does writes. So service A now owns 1, 2, 4, and 6. Nice, well-formed bounded context. Service B owns table 3. That's a nice, well-formed bounded context. And finally, service C owns table 5. That's not so hard. Actually, it is extremely hard. But we're not done yet, because now I've got to do all the various reads. And do you see what's happening? Within a bounded context, I can no longer query your data. I have to ask for it by some sort of means, remotely. And what that means is that the functionality may be able to be separated, but the data cannot be. And because of those data relationships and data dependencies, which are highly semantically coupled and also may be syntactically coupled as well, what it means is, nope, we tried, but because of the data, we've got to keep it a single service. There is one more integration driver I want to close with, and that happens to be workflow and choreography. So let's do another example. Here's our service. We choose to break it up into 4 pieces. However, the problem is those 4 pieces now of services, or those 4 services, are highly semantically coupled. Now, what semantic coupling means is that any given request to that functionality unfortunately requires all that functionality to execute. So those services really, as we split them apart, are like a silly putty or glue, or like just string or gum. A gum is a better example. As you're walking down the street and all of a sudden it's like, oh, and you lift up your shoe and it's all gooey and stuff. That's semantic coupling. All right, whatever, that's fine. Yeah, but we had really good reasons for breaking those services apart. Fine. So yesterday, the user goes into the system, does their updates, responds back in 25 or 150, 1,500 milliseconds. Okay. We did our release of our new microservices breaking apart thing. Same customer, same request, now goes in, and all of a sudden, due to all the latency that occurs because these are all semantically coupled, all of a sudden now it's taking 4,500 milliseconds. It's interesting. Most of us think about latency only in terms of network latency. The amount of time it takes to make a round-trip, RESTful remote call from 2 services. However, that's 1/3 of the latency equation. There's 2 other kinds of latency that are occurring right here. Are the endpoints of your services secure? I hope they are, because if they're not, please meet me next door and give me the URL so that I can actually go in and kind of start hacking away. That's latency, folks. Now, it might be small latency in terms of just validating that you have a web token, or maybe validating that is a valid web token. It might be reauthorizing for a request. So now we have network latency, We have security latency, but there is a third kind of latency I am illustrating up here that causes all of our performance issues. Does anybody see it? Yeah, data, exactly. It's the third kind of latency we forget about. Look on the, I have to do this, left-hand side, the single service. When I go to do that update or that query, how many database calls did I make? One. It's a single join. How many database calls am I making on the other side? This side over here. 4. Because I'm having to go ask for data. That service has to go and retrieve that information. That's called data latency. So all of a sudden now, that's why things get so slow. But we also have reliability and consistency issues as well. Now, when I go to do an update or request and a service is non-responsive, I have to send an error back. I didn't have to do that before. Think about it. What if that were an update? Ooh, now I'm in compensating transaction world and trying to do eventual consistency. Neal Ford and I, are coining the next 8 fallacies of distributed computing. Why is this so much different when we broke things apart? I need to find out where that is. Oh, broke apart is over there. Okay. When it broke things apart over here, why is it suddenly so much different than when I had things consolidated? The answer, 8 fallacies of distributed computing. That's what plagues us now. The network is secure. Latency is 0. Bandwidth is infinite. The list goes on. Neal and I are actually in the process of coining the next 8 fallacies. And we've got number 9 and 10. Number 10 is this. Compensating updates always work. Isn't that great? Whenever we do compensating updates, reverse the transaction. We always make the assumption that it works. And most of the time it doesn't. And now what do? Do I compensate the compensate for the compensation of what I'm trying to compensate before? Now I'm just going to go back to it. Suddenly, monolithic systems look pretty attractive, don't they? We're all going to walk out of here. No more microservices. Yeah. All right. So those are the 2 forces at play for service granularity. And really, getting granularity right, achieving that right balance of granularity, is understanding the trade-offs between these 2 forces, disintegration drivers and integration drivers. All right, wonderful. Well, fortunately, I was asked to kind of speed it up a little bit, and because of anticipation of lots of questions, which we didn't get to do last time. So now I would love to entertain any questions that you have. We have some time for questions, either from yesterday or today, either one. And there's the microphone. Wonderful. Good. I was afraid I was going to be, boy, that must have been a very thorough talk if no one has any questions. Yeah.
Thank you for the presentation. Very interesting. My question is about data dependencies, as integration drivers, yeah? What do you think about data mirroring as a solution to spend less time to the requesting internal server-to-server calls?
So if I understand the question, it was what do I think about data mirroring as a way of resolving the data dependencies? Yeah. Okay, so when we try to access data that we don't own, so the question was about when I talked about those data dependencies and took a look at, let's see, that's probably 55. Oh, yes, there it is. Okay. So the question is related right to here. There it is. Okay. So, yeah, but you could resolve all this with mirroring. And kind of not have the problem then. There's a couple of issues that occur when using those kind of solutions. First of all, it does require that all of those schemas and all those databases in those bounded contexts, let me back up. A microservice is a single-purpose service, separately deployed, which does one thing really well and owns its own data in a bounded context. So, if each service owns its own data, it allows me to say as a service, well, my functionality and my data shouldn't be relational. No, I'm going to use a KV database, or I'm going to use a columnar database. I have my choice of using whatever kind of database I want to either improve the structure and usage of that, or to increase some sort of operational characteristic like scalability or integrity. So the first issue that occurs is that all the DBMS has to be the same if I'm mirroring. So I'm restricted from saying, I really don't want relational though, but I have to stay relational because I'm mirroring to other things that are relational. So that's the first problem. But depending on the database technology and the database tool, with mirroring, I no longer have ownership of my schema. I can't freely change it because it's mirrored to another table in another service in another bounded context. And if I change my structures, which I own, in my own bounded context, I'm now breaking a lot of you who are mirroring my table. Those are two trade-offs. Those are issues, but I'm just saying those are the trade-offs with leveraging things like backend mirroring or trying to manage views in microservices, which is the same kind of problem we have. Who owns the view? I can't change the structure of that view because I break everything. So anyways, that's, it is certainly an option. Good point in finding that and observing that. But it's understanding the trade-offs. As a matter of fact, that was the subtitle of our book, Modern Trade-off Analyses for Distributed Architectures, and the hard parts. And what we try to do is show you what those trade-offs are. We don't have the answer, but we can provide you with what those trade-offs are. So, yeah.
Thank you for the talk, Mark.
Oh, there you are.
I have a question about component-based decomposition and tactical forking. Mm-hmm. What are some tips or objective metrics, so to speak, for judging what is a definable component and what is not?
Wow, fantastic question. Architectural components, as I alluded to yesterday in my talk, are usually manifested through namespaces, package structures in Java, maybe directory structures in non-object-oriented languages. So when you actually create, and I'm just going to use the word namespace, if you're in Java, interpret it as package. If you're not doing object-oriented, interpret it as a directory. But as I add a namespace, what I'm effectively doing is creating another architecture component. So one of these, as a matter of fact, this is a core concept in the decomposition patterns. Because when we try to identify a component and we identify it through the namespace, what happens if I have namespace upon namespace upon namespace upon namespace upon namespace upon namespace, and I've got code all the way down through all those? App.customer, app.business.customer, .notification.sms. I've got code splattered all around there. Where's the component? Well, it's SMS. Yeah, but there's code it needs in all these other sub namespace nodes. Oh yeah, huh? So I can't extract it, can I? Because it's going to look like that gum that I just stepped in on the sidewalk. Everything else gets pulled out with it. So one of the metrics which I use, as a matter of fact, it's a refactoring pattern called flattening components. And the idea is to identify truly definable components in our monolithic or even in our services. We try to push all of the code all of the code to the leaf nodes of the namespace. Now you're saying, yeah, no, you can't do that, Mark, because there's shared code that exists in some of those. That's why we have the code in customer, .letter, .notification, .letter. We have that code in customer because it's shared code. It's objects, it's transfer objects, it's stuff we need. Well, that's fine. Take that code out and put it in another component called .shared code or shared stuff. But this technique of pushing all the code to leaf nodes means that the tail end of your package structure, your namespace, your directory, is the component. And therefore, all that code that does that thing is now consolidated and can be extracted. It could be combined with other components to then be extracted. So that's the metric I typically use, is to say, here it is, here's my test. We talked about testing architecture yesterday. No code shall exist in a root namespace. A root namespace is identified by a namespace that is extended by another node. If I do that metric and that test, it ensures me that all code, shared and otherwise, is pushed out into identifiable components. So that's the test that I typically use. Yeah. And that is, in our book, that is the third pattern. It's called flattening components, and you can kind of read all about that. Or show up next year for the workshop. Assuming I'm invited. I may not be in that case. Well, you can catch me somewhere. Okay. Yeah. Oh, yeah. Looks like there was a question back here. I see a hand up. And and over here, I think there was one.
Thank you. I wanted to ask about, I'm still trying to wrap my hand about fitness functions. So how would I define one for something, for some operational characteristic which is more subjective, like usability or simplicity?
Interesting. So how do you determine? So so I'm going through my mind. There are some things that are kind of more subjective. Agility, simplicity. What was the first one you mentioned? Usability. Yeah, usability. So these are kind of interesting. Again, if you can measure it, you can define it. What would we measure to determine the level of simplicity, which you are absolutely right, is very subjective, in our system? Maybe it's the amount of time it takes to make a code change. The amount of time it takes me to locate a bug and fix it. The amount of time it takes me to add new functionality. Those are some things I can measure to determine the level of simplicity. Usability. Now, usability is an interesting one. Agility. Let's talk about that one first, and then we'll say usability. So agility is the ability to respond quickly to change. Our systems must be agile. We must respond quickly to change because time to market, speed to market, is our most important thing in this company. Yeah, our systems are agile. Can you prove it? What would we measure? Same kind of things. How long did it take me to complete that ticket in Jira? Matter of fact, using something like Jira, I can actually write the fitness functions in Jira because I can trigger on the workflow based on when I mark a ticket as complete, and then it goes to test. And the testing is marked complete, and then it's marked as release. I can measure the time, both in terms of hours and duration, and I can start tracking that. You claim that you moved to microservices to be more agile because it has 5 stars for agility. Yeah. Did it work? Because we can start tracking to see small, medium, large changes. Are we deploying faster? Are we testing faster? Am I able to apply code faster? These are measurements. These are metrics that I can do. Usability is a tough one because here's the question. Is usability an architecture characteristic? Neal Ford defines architecture characteristics as three things. Three things are required for it to be classified as architecture characteristics. So I'm going to channel Neal right now. It specifies a non-domain design consideration. Got it there. Number two, it somehow influences the structure of the system, the structure. And then number three, it's critical or important to the application success. Now, I like the third one the best because too many times we say, oh yeah, performance. And we focus on performance all the time. I mean, as a developer, it's the first thing on our mind. Does the business even care about performance? Our SLA is 2,000 milliseconds. And we're now processing at 800 milliseconds. We don't have to optimize for performance. Pre-optimization of performance is one of the big anti-patterns I see in a lot of teams. Because there's more things the business cares about besides performance. Where was I? I got on a little rant. Oh, yeah. So the second piece, usability. When we think about usability, it's the flow of the screens. It's really UX stuff, isn't it? Doesn't much have to do with architecture. However, usability as an architecture characteristic refers to how or what means can I access my data. I want to check my bank account balance. How do I do that? Oh, it's simple, Mark. Just give us a call, ring us up, and give us your account number, and we'll tell you your balance. Really? I don't even use my phone for a phone. And secondly, my account number? Oh yeah, let me give that to you. XXX-XXX-XXX52. You don't even tell me what it is on my statements. It's all masked. Oh, right. We'll create a website. Yeah, great. How often am I at my computer? Oh, there it is. All of a sudden I looked over next to Michael and I'm like, where's my computer? Oh, it's up here. Maybe it's mobile. Maybe it's on the watch, a little widget that I can turn like this and it always shows me the balance. One better from usability. We're developing a chip that we're going to plant right in your brain so that all you have to do is just say, wonder what my balance is, and you know it. That's usability from an architectural standpoint because I am actually changing the structure of my system with all those different access means. So yeah, usability is a tough one. I guess I could measure that by the number of complaints or the number of uses of the chips. I mean, we spent about 4 million euros to develop those chips. How many people are using them? 2. There's a metric. Great question, though, because you're right. A lot of these are subjective. So, I think we have time for one more question. Ekaterina, is that right? Or yeah, one more question, and I'll make sure the answer is short.
Thank you very much. And the question is, what you're talking about, and many other presenters also, about modifying existing systems. But when we're starting from scratch, and most of the metrics which you're talking about is unavailable because we not have code, we not have statistic and nothing. So what approach we should take, in your opinion? We should prototype everything, or we should believe our intuition?
Yeah. I have 2 answers for that. The first is to, at the beginning, to leverage qualitative versus quantitative analysis. I don't have numbers yet. I don't have requirements of our SLAs, but I know we need to scale. I don't know what those numbers are yet, but we do need to scale. Qualitative analysis says I've got a trade-off to make. This option is more scalable than this option. I don't know by how much, but it is more. And I start making those kind of decisions based on qualitative analysis. Once I start getting those numbers and those requirements, empirical numbers, now I can use quantitative analysis. But it leads to another really good point. This is a conversation I was having yesterday. So when should you write these fitness functions? So let's say we start moving to quantitative, I always get those mixed up, quantitative analysis. I can start writing fitness functions to say we need to scale to 120,000 users. I can write those during the development cycle. I can use those as triggered fitness functions to see how close I am. As a matter of fact, Neal Ford, who was going to be here on this stage, was actually going to introduce the concept of fitness function-driven architecture, which is exactly that. We do test-driven development a lot. What better way to write code than to write the test, have it fail, write the functionality, and now it works. That proved I did a good job on this. Let's do the same thing with architecture. Identify those fitness functions from a qualitative standpoint, and then once we have those numbers, use quantitative analysis. Have the fitness functions in a development environment maybe running continuously, or maybe it's triggered, but yes. And the cool thing is this. Now I've got the fitness function, so when we release, it just goes into production as well. Yeah, so that would be an approach. So I do think we are out of time, but thank you all so much. I'm so sorry Neal wasn't able to be here, but I did want to at least kind of step in his place so that we did have a talk for today. So anyways, thank you all so much.